Hello everyone, this is Mrs. Hanson. I am your instructor for Chemistry for Health Professions Semester 2. You'll commonly hear me call that course with the letters G-O-B, and that responds right to your chemistry book that says General, Organic, and Biological Chemistry as well. Of course, in your first semester, you focused on general chemistry, and in our second semester, our journey begins in organic chemistry, and that's our topic of Chapter 11, Organic Chemistry, and we carry that on through to the end of the term where we introduce basic concepts of biochemistry as well. So in our second semester, our focus is on organic and biochem. I wanted to remind you, if you've not yet had a chance to complete the course information module, you should do so immediately before proceeding with this lesson. The e-learning chemistry course is a robust, complementary kind of companion site, if you will, to our online and in-class version of our course. So just to keep in mind, you want to read through the course syllabus, view the course calendar. We have very firm due dates, and so you want to make note of those immediately and get them in your calendar. There's some study tips for chemistry students. You want to enroll in the McGraw-Hill Connect site. That's our companion homework site. And read that information about how our quizzing and testing will occur remotely through our proctoring service called Proctorio. In that syllabus, you'll read that it's $20 per term for your unlimited proctoring service. So go ahead and just read information about that at this time. When you enroll will be when you open Chapter 11 quiz, the first quiz in our course. You have your credit card ready and you'll have to enter into your information there. And of course, you need to use your CAM scanner app to turn your smart device into a scanning document. So read and practice using your CAM scanner app. So go through that course information site, and when ready, let's begin our Chapter 1. Keep in mind, as we begin Chapter 11 in our first chapter together, you will need your Chapter 11 lecture guide note pack printed out in front of you. We will complete that together as I deliver my lessons. So the notes are complementary to the slideshow that you are going to work problems with me and present material. And when the completed packet is ready to turn in, you use your CAM scanner app to turn it into a single document, a PDF form, and submit that into the Dropbox for Chapter 11's notes. So it is your job to print and complete the Chapter 11 note pack as we progress through our lessons together. Chapter 11, as I mentioned, introduces organic chemistry. Chapter 11's title, Introduction to Organic Molecules and Functional Groups. It is a preview of all the chapters really that are coming our way this term. Consider for a moment the activities that occupied your past 24 hours. You likely showered with soap, drank a caffeinated beverage, ate a few meals, and traveled in a vehicle that had rubber tires and powered by fossil fuels. If you did any one of these, your life was touched by organic chemistry. In Chapter 11, we learn about the characteristic features of our organic molecules. As we look at our learning goals, our learning outcomes are also presented in our e-learning platform. The first reads, to recognize the characteristic features of organic compounds. What distinguishes organic from inorganic compounds that you spent time studying in first semester? We need to review how to predict shapes around the atoms in organic molecules. I know in last semester you worked with what we called the VSEPR theory, valence shell electron pair repulsion theory, and that really gave us the geometry for molecules. So we'll be reviewing molecular geometry from semester 1. We'll practice writing shorthand methods drawing organic molecules. We'll recognize those functional groups and understand their importance. We'll distinguish organic from inorganic compounds. We'll have to determine if organic compounds are polar or nonpolar, and determine the solubility properties of organic compounds. Just remember that, generally speaking, likes dissolve likes, and we'll review polar with polar, nonpolar with nonpolar, but never the two shall meet. And then the last one, of course, is going to be a reading assignment from your text. You'll read to determine about vitamins being fat or water soluble. So that kind of outlines or maps our journey for Chapter 11, the first of our Semester 2 organic chemistry journey together. And remember, these are the assigned activities and assessments, and really you can count on these for every chapter. You're going to use these videos or in-class sessions, depending on if you're an online student or in-class student, to complete your lecture guide note pack. Remember, you are responsible for printing for each chapter, filling in the note pack from the presented lectures and from your text. You'll compile all those pages into a single document, use your CAM Scanner app, and submit into the Dropbox for grading by the assigned due date. Remember, those due dates are firm. Make sure you've checked out your calendar. These are graded assignments worth 30 points in your attendance and participation category. So, of course, the first thing we'll do together is fill out our note pack and present lessons. The second assignment is to complete your Connect homework, which is on the McGraw-Hill Connect site by the assigned due date. They are 15 points in your homework category. And of course, the third for each chapter is to complete your proctored multiple choice quiz by the due date. That again is worth 15 points in the chapter quiz category. When I say proctored, remember our proctoring service is Proctorio, and you need to learn more about that by either reading the syllabus or course information module. So, with our note packs in hand, let's begin our first section, 11.1, Introduction to Organic Chemistry. And you'll notice your note pack is simply asking you to fill in some blanks, record some notes, draw some structures, and do practice problems with me together. So in our first introduction section, we define the term organic chemistry. It is the study of compounds that contain the element carbon. Carbon, of course, is the key component of all organic compounds. Organic chemicals affect virtually every aspect of our lives together. Some organic compounds are natural sources and some are from synthetic sources. These products include clothes, foods, medicine. The entire pharmaceutical industry relies on organic chemistry. Fossil fuels such as gasoline, refrigerants, and soaps are all composed of organic molecules. We can see examples of natural sources being cotton, wool, or silk. And others that are examples of synthetic would include such materials as nylon and polyester. We can see examples of some of these organic molecules from contraceptives, plastics, antibiotics, a synthetic heart valve, or all a myriad of other materials include vastly different compounds, and yet all underlying this umbrella known as organic chemistry. They contain the element carbon, and that is key, that all of these compounds, being either from life or from synthetic value, come from carbon. Some compounds that contain the element carbon are not organic compounds, and we need to know these as well. Examples include carbon dioxide, which has the molecular formula CO2. Carbon dioxide contains the element carbon, yet does not qualify as an organic molecule. Sodium carbonate. Sodium, of course, is a +1 ion. Carbonate, CO3, carries a -2 charge, and so when we write out its formula, we get Na2CO3, sodium carbonate. Notice this carbonate contains carbon, and yet is considered not organic. And the last is commonly called baking soda, sodium bicarbonate. The bicarbonate polyatomic ion is NaHCO3 for sodium bicarbonate. And so here's our first practice. Which chemical formulas represent organic compounds and which represent inorganic compounds? And these match your examples. Those examples are asking you to simply write on the line, organic or inorganic. Pause the video and complete those, and when ready, come back to check. Welcome back. You must have answers. Let's check them out. In our first compound, I can clearly see that there's a carbon along with a hydrogen that indeed meets the criteria for being considered an organic molecule. We will learn carbon with a number 6 associated will have a prefix hex, as in hexane or hexene. The second example is a water molecule. I see no carbon at all, so I bet you wrote inorganic. The third is potassium iodide, Ki, potassium iodide. No carbon there, so I'm sure you wrote inorganic. Here we have magnesium sulfate. Again, that's an ionic salt, no carbon, so that is an inorganic compound. CH4O, yes indeed, this meets all the criteria of being organic. It contains carbon, as well as hydrogens and oxygens. And the last one I see is sodium hydroxide. Remember that polyatomic ion, hydroxide? That's a base. This is an inorganic compound. I see no carbon there at all. So a nice opportunity to just check what is considered organic versus inorganic. And here I've typed out, just for a double check, your answers against mine. In our second section, we'll look at the characteristics of organic compounds. Some examples of organic compounds would include methane, which is the component of natural gas, and ethanol, which is the alcohol present in alcoholic beverages. Notice that methane, the main component of natural gas, has a central carbon and 4 single covalent bonds leading out to each hydrogen. It has a molecular formula of CH4, and we can see its structural formula, where we can see the bond connectivity between the atoms. C is the central atom leading out to each of those 4 hydrogens. It's a perfectly symmetrical molecule. Here we see ethanol. I have 2 carbons in a chain. Notice I have 2 carbons. Maybe I should change color so you can see. Here's the first, here's the second, connected by a single bond. The first of those 2 carbons connects to 3 hydrogens to complete its octet. Here these hydrogens are attaching to the second carbon, and we have a functional group of OH. We will learn that that functional group OH, hydroxyl, represents the functional group of an alcohol. Ethanol is the name of a 2-carbon alcohol. Here that OL ending, kind of seeding future lessons for us. What do we notice in common? Well, I can see carbons attached to hydrogens, along with this example contains a functional group. We have a simple methane and a functional group in the alcohol known as ethanol. Some examples of organic compounds continued, because capsaicin is responsible for the spiciness of peppers and is used for topical pain relief. Look how complex this molecule is. And yet what do we see in common? We see a lot of carbons bonded to hydrogens. We see some oxygens present. Here I even see a nitrogen present in this compound as well. Sometimes I notice that there's C single bond OHs, and sometimes I notice that C can be double bonded to oxygen. Here I'm even noticing that a C can be double bonded to another carbon. And yet the heart of this molecule is indeed organic, with all of those elements present meeting the criteria of an organic molecule. And one more example, caffeine. That's the stimulant found in coffee, tea, cola, beverages, and coffee. I have some on my desk right now. Caffeine has some nitrogens, a carbonyl carbon. We can see C double bond N, we see C single bond N, and yet the heart of this molecule, no matter how complex, is that it has carbon as its backbone. With these examples, we're getting an idea that organic molecules, whoops, I hit the wrong slide, organic molecules all contain hydrocarbons. We're ready to flip our page over. All organic compounds, as we've witnessed, contain carbon atoms, and most will contain hydrogen atoms to complete the carbon's octet. Notice something that carbon always has 4 covalent bonds. Carbon will be attached either by 4 single bonds, or it could have 2 single bonds leading to a double bond, or it could have 1 single bond leading off to a triple bond. But notice that no matter what arrangement, they always have 4 bonds to complete its octet. Hydrogen always forms 1 covalent bond. And that secret lies in remembering from first semester the Lewis dot structure for carbon. Since carbon lives in group 4A, it has 4 valence electrons, so therefore we can see 4 dots around it, 4 open spots for bonding. Hydrogen, of course, lives in group 1A. Group 1A tells me it has 1 valence electron. It has room for just 1 open spot for bonding. So carbon, always 4 bonds, hydrogen, always 1 bond. And when we designate these bonds, a shared pair of electrons gets replaced by a line to represent the shared pair. So this represents what we know as a single covalent bond. Carbon forms single, double, or triple bonds to other carbon atoms. 1 shared pair is a single line, each carbon forming 4 single bonds. We're going to draw in our boxes there the Lewis dot structure for ethane, a 2-carbon hydrocarbon. We're going to learn this is called an alkane, since all of the bonds are in this compound are single bonds. Ethane, drawn with its shared pair structural lines, and ethane, drawn with its Lewis dot structure, are being drawn onto your note page so that it's reinforcing what we refer to as the 4 bonds of carbon being all single. Or when we look at ethylene, ethylene contains a double bond in the structure. I want you to draw both in terms of the Lewis dot structure just to help us reinforce that a double bond has 4 electrons or 2 shared pair. So we'll draw the Lewis dot structure as well as the line structure. And in the last example, we have something called acetylene. Acetylene contains a triple bond. But again, it doesn't matter if it's a single, double, or a triple. They all have 4 bonds leading out from each carbon atom. We're emphasizing in Lewis dot structures that we see 3 shared pairs. Double bond means 2 shared pairs of electrons, and this is 1 shared pair in that ethane molecule. We have emphasized that carbon requires 4 bonds. Each carbon atom has 4 bonds, being all single, 2 single and a double, or 1 single and a triple. Some compounds have chains of atoms, while other compounds have rings of atoms. If we see a 3-carbon structure, notice I can number those carbons, carbon 1, 2, 3, such as a molecule of propane. This again falls into a functional group of a family called an alkane. Alkanes contain all single bonds. Carbon 1 needs 4 bonds, so we can see 3 hydrogens are required to complete its octet, with the 4th one leading to the 2nd carbon. Since carbon 2 is attached to 2 other carbons, it requires only 2 hydrogens to complete its octet. And propane, the number 3, since it's attached to just 1 other carbon, requires 3 more H's to complete its octet, with the molecular formula of C3H8. Now, if we were to take these particular, let's just erase this. If we were to take those compounds, carbon 1 and carbon 2, and carbon 1, 2, 3, carbon 1 and 3, and attach carbon 1 and 3 to form a cyclic structure. To do so, we have to remove the terminal hydrogens to create a site of attachment. So notice that removing 2 hydrogens gives us a formula of a cyclic alkene with 2 less hydrogens, C3H6. And again, just to emphasize, when we remove hydrogen on the first carbon and hydrogen on the third carbon, those bonds are left open now to create a site of attachment between carbon 1 and 3. So we can have cyclic structures or straight chain structures and still call them alkenes since they are all single bonds. Some organic compounds contain other elements as well. Any element such as carbon and hydrogen, which are the main elements of an organic compound, but if we do see other elements involved, they are referred to as a heteroatom. Hetero, of course, is a prefix that means different. So if it's not a carbon or not a hydrogen, we call it a heteroatom. Each heteroatom forms a characteristic number of bonds determined by its location on the periodic table. So let's review some common elements in addition to carbon and hydrogen we could find in organic chemistry. Some common heteroelements include nitrogen, which lives in group 5A. Nitrogen would have a Lewis dot structure showing 5 valence electrons. We could see oxygen. Oxygen lives in group 6A. So when we consider the Lewis dot structure for oxygen, we see that it has 6 valence electrons. Fluorine, chlorine, bromine, and iodine are all known as the halogens. Halogens often get abbreviated as an element X, where that is just a generic symbol to represent any of the halogens, fluorine, chlorine, bromine, and iodine. And just to remember that any element in 7A would have 7 valence electrons around its symbol. And remember, X is a generic symbol to represent fluorine, chlorine, bromine, or iodine. And now you can see when you examine the Lewis dot structure how many open spots for bonding each of these elements has. Nitrogen needs to form 3 bonds. Oxygen needs to form 2 bonds. And any halogen has room to form just 1 bond. Now remember, forming 3 bonds for nitrogen could be 3 single bonds, or could be a double and a single, or could be a triple bond. All of those meet the requirement of having 3 bonds. Same for oxygen. If oxygen needs 2 bonds, it could be both singles, or oxygen can also form a double bond and still fill its octet. And remember, a halogen has only single bonds because it only has room to attach with 1 bond to complete its octet. So the number of bonds plus number of lone pairs must always equal 4. In other words, 1, 2, 3, 4 for the halogen, 1, 2, 3, 4 on the oxygen, 1, 2, 3, 4 for nitrogen, so that we complete the octet of each of those elements. Characteristics of organic compounds continued. We're just kind of filling in some practices here. Here we notice that hydrogen, the number of bonds is always 1 with never a lone pair. Carbon must always have 4 bonds and it will never have a lone pair of electrons. Nitrogen will have up to 3 bonds and always 1 lone pair when it's completed its octet. Oxygen has room for 2 bonds and 2 lone pairs. And any halogen has 1 bond and 3 lone pairs. And we practiced that on the previous slide, just recognizing from the Lewis dot structure based on where it lives in the periodic table. And I would say the most common heteroatom is a carbon to oxygen double bond. So the most common multiple bond you'll find in any organic molecule is a C double bond O. Now that doesn't mean that it always has to be a double bond, because clearly we saw a functional group of an alcohol had a single bond to the carbon and oxygen, but it can also form a double bond, and we're going to learn that this is called a carbonyl functional group, a C double bond O. So here we have an alcohol functional group that contains a single bond, and here we have a carbonyl functional group that contains a double bond. So what we're really working on is just practicing how many bonds and lone pairs are needed to complete the octet. And those secrets just lie on finding where the element lives on the periodic table. So let's practice. Draw in all the hydrogens and the lone pairs in each of these compounds. I encourage you to pause the video, try these, and when ready, come back to check your work. Don't cheat yourself of the practice. The learning deepens when you pause, try them, and check. All right, welcome back. Let's check our work together. In compound number 1, we know that carbon requires 4 bonds. So I can clearly see that I have to fill in 3 hydrogens to satisfy that first carbon's tetravalent. That's a vocabulary word. Tetravalent means that it has to have 4 bonds. So I have to add 3 hydrogens. Here we see that carbon number 2 also requires 2 hydrogens to complete its 4 bond requirement. And this is a halogen. Remember, the halogen comes from group 7A. They're only allowed 1 bond because a halogen has 7 valence electrons. And so when I form that single bond between the carbon and the chlorine, I have to represent 3 sets of lone pairs to complete the chlorine's octet. So there's our first structure, drawing in all the H's and lone pairs to complete the octet of that carbon skeleton. Let's examine question 2. The skeleton gives me a C, single bond C, to a double bond O. Each carbon requires 4 bonds. The first would require 3 H's to complete its octet. Now, examining this carbon, it already has 3 bonds, 1, 2, 3. So it only requires 1 more hydrogen to complete its octet. And remember, oxygen, it can form 2 bonds, and it did so already with a double bond to carbon, but it also requires 2 sets of lone pair electrons to complete its octet. So there's our structure for the second compound. And number 3, we have a C to single bond C to triple bond N. Each carbon forms 4 bonds. So I need to include 3 single bonds to satisfy the tetravalent requirement of that first carbon in the line. The second carbon already contains 1, 2, 3, 4 bonds. It does not receive any hydrogens. And nitrogen, if you remember, it lives in group 5A. It can form up to 3 bonds. It has done so with that triple bond, but it also requires a pair of electrons to complete its octet. And there's our perfect structure for number 3. How'd you do? There's more to practice. Flipping to page 4, pause the video, do the exact same thing as additional practice, start the video when ready, and we'll check our work together. All right, welcome back. Let's check. Letter A, I have a carbon to carbon single bond to a double bond back to a single bond. We need to fill in hydrogens to complete each octet. Remember the rule, carbon has no lone pair electrons, but it does require 4 bonds. So just to number these carbons so we can keep track, that's a 4-carbon chain. Our first carbon will require 3 hydrogens to complete its structure. The second carbon already contains 3 bonds, so it requires 1 more hydrogen. Same for carbon 3, it has 3 bonds already, so we add 1 more hydrogen. And finally, at the last carbon, we complete the tetravalent requirement with 3 hydrogens attached. Each carbon now contains 4 bonds. Some are multiple bonds to carbons, all the rest are single bonds to hydrogens. Letter B offers us 3 single bonded carbons leading up to an oxygen with a single bond. Now remember, oxygen, it requires 2 bonds or 2 sets of lone electrons. So this is an unusual case because I'm only seeing a single bond. So remember, here we have 1, 2, 3, 4, 5, 6. That's our Lewis dot structure. And so, quickly we can complete the octets here of carbon. Here's 3 more. But what are we going to do with the C single bond O? So clearly we can see if we require 2 bonds on the oxygen, it must also be leading to another hydrogen to complete the second bond requirement. And this carbon would also require a hydrogen to complete its 4 bond requirement. So here this led to a carbon, this had to lead to a hydrogen to complete the octet of that. Remember, this functional group we're learning is called an alcohol. Letter C. This offers us 3 carbons in a single chain, but now it leads to a double bond O. We're learning quickly that carbon completes its octet with hydrogens, so I can complete those at the terminal ends on each side with 3 single bonded H. Since this oxygen already has the 2 required bonds, all I need to do is add in its 2 sets of lone pairs. And this middle carbon already has 4 bonds, so there's no hydrogens needed on carbon 2. That represents our perfectly drawn structure for letter C. Let's continue on to try letter D. I have C, single bond to C, single bond to N, single bond to C. Carbon 2 has an oxygen, double bonded. Taking care of the first carbon will complete its requirement of 4 bonds by adding 3 hydrogen singles. Notice this carbon already contains 4 bonds, so it's done. And the end carbon, I can quickly complete its requirement by adding 3 hydrogens. Now, remember oxygen, it requires 2 bonds and 2 sets of lone pair electrons. So I can complete its requirement by adding 2 sets of dots. This carbon here has 4 bonds, so we're done. What about the nitrogen? Remember, nitrogen lives in group 5A, and so that said it needed 3 bonds and 1 set of lone electrons. So right now it has 2 bonds, it requires a lone pair, and to complete its octet, it's going to need a hydrogen to satisfy 3 bonds and 1 lone pair. And letter E gives me a cyclic structure where oxygen and carbon-carbon are all in a little triangle. Carbon requires 4 bonds. It's going to need 2 hydrogens to complete the octet. Same story here, this hydrogen and this hydrogen single bonded back to that carbon. And the oxygen has 2 bonds. All it needs to complete its requirement are 2 sets of lone pairs. I think additional practice in your homework awaits for you, but it's easy, just a little practice and repetition and you'll find these quite friendly. I'll pause the video here And when ready, you're going to come back for the next lesson. We'll look at Section 3, Shapes of Organic Molecules, and review some bond angles and VSEPR theory.